All right, so let's talk about motion. Like, really think about it. What does it actually mean for something to move?
Mm.
We see things moving all the time, but, have you ever really stopped to consider what's going on there?
Yeah, I mean, it seems simple at first glance,
Yeah.
right?
But the more you think about it, the weirder it gets.
Oh, absolutely. Like, how do we even know something is moving?
Exactly. And this is something that's, it's a question that's puzzled philosophers and scientists for centuries, going all the way back to the ancient Greek.
Oh, yeah, for sure. And at the heart of it is this kind of fundamental debate. Is motion, is the space that motion happens in, is that a fixed thing? Like, is there an absolute backdrop to reality? Or is it all relative? Is it just about how things are moving in relation to each other?
Right. So, like, if I'm sitting here in my chair, am I actually moving or not?
Well, it depends. Relative to the Earth, you're stationary. But relative to the sun, you're hurtling through space at thousands of miles per hour.
Well, my head's spinning already. And this isn't just like some kind of, abstract thought experiment.
Oh, no, no.
This has real implications for physics, for our understanding of the universe, for cosmology.
Right. I mean, this gets into questions about, the nature of space and time itself.
Yeah, it's deep stuff.
It is. It is. And we're going to be looking at, some of the heavy hitters in this debate.
Oh, yeah, we're talking big names here.
The big names. Aristotle.
Descartes,
Newton.
Leibniz,
Yeah.
all grappling with these foundational questions about space, time, and motion. And we're going to be doing this deep dive using the Stanford Encyclopedia of Philosophy as our guide.
It's a great resource.
Yeah. So we're really going to be acting as philosophers ourselves, digging into these ideas and seeing, what were the core disagreements, what were the arguments, and how did these thinkers shape our understanding of reality, basically.
Yeah, I'm excited to dive in.
Let's do it. So let's start with Aristotle, the OG philosopher.
Right, the OG.
He had this very intuitive view of the world. He saw that things moved in certain ways based on their nature.
Right, so like heavy things fall down, light things rise up. That was just kind of their natural tendency.
Yeah. He believed that this wasn't caused by some external force, but it was something inherent in the objects themselves.
So like a rock just like wants to go down. It's in its nature.
Yeah, like it's got this built-in direction, I guess.
Right. But of course, this whole system relies on there being a clear up and down in the first place.
Yeah, how did he define that?
Well, for Aristotle, up and down were determined by an object's position relative to the center of the universe.
Okay.
And he believed that the center of the universe coincided with the center of the Earth.
So like everything was drawn towards the center of the earth.
Yes. Heavy things would move towards the center, light things would move away from it. And this wasn't just about changing location relative to something else. It was this, inherent tendency tied to an object's very nature and, the structure of the cosmos itself.
Okay, so I see where you're going with this.
Mm-hmm.
This center, this absolute center of the universe, is that what defined motion for Aristotle?
Well, it's interesting. There's some ambiguity there.
Okay.
While he believed the universe's center was at the same place as the Earth's center, they weren't, identical.
What do you mean?
His reasoning was that Earth itself is heavy. So if it wasn't already at the center, its nature would compel it to move there.
Oh, I see.
Right. So the center isn't defined by the Earth.
Okay, so maybe it's more like this tendency towards the center.
Yeah.
Was that an absolute then?
Yeah.
Like not just towards a specific object?
That's a good point. It seems like it. However, Aristotle also suggests in his work on the heavens, he suggests that the center might be determined by something else, actually.
What else is there?
The outermost sphere, the fixed stars.
So like the entire universe is kind of centered around this sphere of stars.
That's how he saw it. And
Right.
if that's the case, then up and down, those directions become relative to this, cosmic boundary.
So it's not as simple as just saying the earth is the center.
Right. It's a bit of both. The
Yeah.
center, isn't just the Earth, which kind of hits at this absolute direction.
Right.
But its determination might involve the fixed stars, which then kind of brings in this relational element.
Right. So even though he didn't explicitly frame it as absolute versus relative, you can see him grappling with these ideas.
Exactly. Trying to define these fundamental directions and place in the universe.
Yeah. Okay, so that's Aristotle.
Yeah,
Now let's fast forward a bit
quite a bit.
to Descartes.
Yeah, so Descartes, he came at this whole thing from a very different perspective.
Yeah, completely different philosophical framework.
Exactly. So in his Principles of Philosophy, he makes this really interesting argument. He says that the essence of matter like what matter fundamentally is extension, which
Extension.
is basically just having size and shape taking up space.
Yeah, so like you could imagine a piece of matter, um, losing its color, losing its smell, all its other properties,
Right.
but it still has to take up space.
Exactly. You can't have a piece of nothing that occupies volume. It just wouldn't make sense.
Right, right. So extension is kind of like the fundamental, essential property of matter.
Precisely. But here's where Descartes' argument gets really wild.
Okay, I'm intrigued.
He then goes on to say that this extension, this property of matter, is the very nature of space itself.
Whoa, so what you're saying is matter is extension, space is extension, therefore matter and space are the same thing.
Boom. You got it.
That's
Yeah.
a pretty big philosophical leap.
Oh, it's huge. But think about the implications. If there's no distinction between matter and space, then there can't be any empty space.
So no vacuum.
No vacuum. The universe is just like completely packed with stuff, different formations of this extension, just constantly moving and swirling around.
So like a cosmic soup?
Kinda, yeah, like a bucket of water with different currents moving through it. He actually used the term hydrodynamical to describe the universe.
Hydrodynamical.
Yeah.
Fancy. Okay, I'm starting to see a problem here.
Oh, yeah.
If a body is the space it occupies, how can it move to a new place?
Right. Like, where does it go? The space has to move with it, right?
Yeah, it's a real brain twister.
Yeah.
So how did Descartes, how did he get around this philosophical puzzle?
Well, his solution was to say that all motion is relational,
Relational.
meaning that motion is about the movement of bodies relative to one another, not about a change in the space they inherently are.
Okay, so it's not like a car is moving through some kind of empty space.
Nope.
It's more like the car is changing its position compared to, the road, the trees, other cars.
Exactly. It's all about relationships. But here's the thing. Descartes didn't think all these relative motions were created equal.
Oh, interesting. So there's degrees of motion?
In a way, yeah. He came up with a few distinctions.
Okay.
So first, there's what he called change of place,
Change of place?
which is just simple motion relative to any reference point you choose. So like my pen on the desk, it's technically moving relative to, the sun or a distant galaxy,
Right.
even though it's perfectly still relative to me.
Yeah, that makes sense.
So in that sense, no motion is really more fundamental than any other. It just depends on your frame of reference.
Okay, so that's change of place. What's next?
Then he talked about motion in the ordinary sense.
Ordinary sense.
And this is closer to how we usually think about motion. Like when we say something is moving because its movement is caused by some action or force.
Okay.
So a boat moving through the water because of its engine, that's motion in the ordinary sense. But a passenger sitting on the boat, we wouldn't really say they're moving.
Right, because they're at rest relative to the boat.
Exactly. So this distinction kind of aligns more with our everyday experience of the world.
It makes intuitive sense.
Yeah. But then Descartes also came up with this, well, it's kind of a controversial one.
What?
He called it motion properly speaking.
Motion properly speaking.
Yeah, and he defined it as the transfer of a piece of matter from being surrounded by one set of contiguous bodies to being surrounded by another set of contiguous bodies.
Contiguous meaning?
Touching, like in contact with.
Right.
And since a body can only be in contact with one set of surroundings at any given moment, Descartes argued that this provided a unique standard for motion.
I see. So it's not just about how you're moving relative to something else.
Right.
It's about your actual physical contact with your immediate surroundings.
Exactly. And that this was, for him, this was the most crucial kind of motion.
Really? So even though he was arguing for relational motion, this motion properly speaking, it sounds a lot like he's trying to sneak in a little bit of absolute motion.
It does, doesn't it? It's like, despite all his talk about relativity, he still wanted to find some kind of true, privileged sense of motion.
Right, like a kind of motion that's not just relative to something else, but it's a property of the object itself.
Exactly. And this leads to a really interesting question. Did he actually believe in this motion, properly speaking, as a fundamental part of his physics? Or was it more of a strategic move?
Strategic. How so?
Well, remember, this was the time after Galileo, when the church was cracking down on any ideas that challenged the geocentric view of the universe.
Yeah, the whole Earth at the center thing.
Right. So some scholars have suggested that Descartes might have emphasized the ordinary sense of motion, like the idea that the Earth is being carried by a vortex as a way to avoid, getting in trouble with the church.
Ah, the classic, I didn't really mean it defense.
Right. But if we actually look at his mechanics, his laws of motion, and we try to interpret them through this ordinary sense of motion, things start to get a bit messy.
How so?
Well, let's look at his rules of collision, for example.
Collision, like when things bump into each other.
Exactly. So one of his rules suggests that if two identical balls approach each other at the same speed, they'll just bounce back with that same speed.
Okay, that makes sense.
But then another rule seems to imply that if the two balls approach each other with the same relative speed, but they have different individual speeds, they might actually stick together.
Wait, what? How can that be?
Yeah, it's a bit strange, right?
It's like the same interaction is producing different results just because we're describing it differently.
Exactly. And if only relative motion mattered, then those two scenarios should be fundamentally the same.
Right. But Descartes is saying they're not.
Nope.
Ah.
And this suggests that he was actually relying on a more fundamental sense of motion, maybe this motion, properly speaking, to make his mechanics work.
Okay, so this motion, properly speaking, wasn't just some kind of side note.
Right. It was actually a key part of his philosophy of physics.
And there's a philosopher, Daniel Garber, who's actually argued that motion, properly speaking, was the operational definition of motion in Descartes' physics.
Yeah, Garber makes a compelling case. He shows how a lot of the apparent inconsistencies in Descartes' collision rules can be resolved if we interpret them through this lens of motion, properly speaking. Like, for example, Rule 1, the one about equal and opposite reaction, that would apply when bodies have equal and opposite proper motions relative to their immediate surroundings. And then Rule 6, the one about bodies moving together, that would apply when their proper motions relative to those surroundings are different.
Okay, so it's like even though Descartes is talking about relational motion, he's still got this underlying notion of a more absolute kind of motion that's driving his physics.
Exactly. And that tension between relationality and absoluteness is something that, it really comes to a head with Newton.
Oh yeah, Newton, the big man himself.
The man who, gave us the laws of motion that we still use today.
Yeah, he basically laid the foundation for modern physics.
He did. But even Newton, his views on motion have been the subject of, a lot of philosophical debate.
Right. And it's important to remember, he wasn't just starting from scratch. He was building on, but also reacting against, the ideas of the thinkers who came before him, especially Descartes.
Oh, absolutely. And one of Newton's most famous thought experiments, it directly addresses this question of absolute versus relative motion.
Oh, yeah, this is the one with the bucket, right?
That's right. Newton's bucket. It's described in his work De Gravitatione and also in the Scholium to his Principia.
Okay, set the scene for me.
Okay, so picture a bucket filled with water. It's hanging from a rope that's been twisted up.
Okay, I'm picturing it.
So first, you let the bucket hang still, and the surface of the water is flat.
Yeah, makes sense.
Then you let go, and the bucket starts to spin.
Okay.
Now, at first, the bucket is spinning, but the water inside hasn't really caught up yet. It's still relatively still.
All right.
And the surface of the water is still flat.
Okay.
But then, gradually, as in the water starts to spin along with the bucket, something interesting happens.
What happens?
The surface of the water becomes concave.
Concave, like it dips down in the middle.
Exactly. And the water actually rises up the sides of the bucket.
Oh, yeah, I've seen that. It's like a little whirlpool in the bucket.
Right. And this is where Newton's argument comes in. When the water is spinning along with the bucket, it's at rest relative to its immediate surroundings.
Yeah, it's not moving relative to the bucket.
But according to Descartes' motion, properly speaking, that means the water isn't actually moving.
Right, because it's not changing its contact with the bucket.
Exactly. But clearly something is happening. There's a real physical effect. The water is changing shape. It's rising up the sides of the bucket.
Yeah, you can't just explain that away by saying the water isn't moving.
Right. And what's even more interesting is that the opposite is true as well. When the bucket first starts spinning and the water is still flat, the water is moving relative to the bucket.
Right, because it hasn't started spinning yet.
But there's no concave shape. There's no change in the water's surface.
So Descartes' motion, properly speaking, doesn't really seem to capture what's going on here.
It doesn't. It's almost like it's the opposite of what we'd expect.
Yeah, it's backwards.
And Newton makes another important point. He says that the height the water climbs up the sides of the bucket, that's a direct measure of the rate of rotation.
Okay.
So a higher climb means a faster rotation.
So it's quantifiable.
Exactly. And Newton argued that for any given height, there's a unique rate of rotation. But if motion was just, change of place relative to some arbitrary reference point, then that rate wouldn't be unique.
Right. It would depend on how that reference point was moving.
Exactly. So the fact that we get this like consistent, measurable outcome, the water's shape, and it's tied to a specific rate of rotation, that suggests that there's something more to motion than just relative change of position.
Right. It's like there's some kind of absolute motion going on.
That's exactly what Newton concluded. He argued that this, mechanically significant motion, especially rotational motion, it wasn't Descartes' proper motion. It wasn't just change of place. It was something else entirely.
So what was
Motion relative to absolute space.
absolute space? All right, let's unpack that. What did Newton mean by absolute space?
Well, for Newton, absolute space was this like unchanging three-dimensional Euclidean space.
Euclidean space.
Basically a grid, a fixed container for the universe.
Right, so it's not made of anything. It's just this, like, background framework.
Exactly. It's the stage on which all the cosmic drama plays out. And unlike Descartes' space, which was just, moving matter, Newton's absolute space was this distinct, immutable backdrop.
Okay, so it exists independently of any matter.
Right. And true motion, for Newton, was motion relative to this absolute space.
So when the bucket is spinning, it's not just spinning relative to the water inside.
Nope.
It's spinning relative to this absolute space.
Exactly. And that's what causes the water to change shape.
Okay, so I think I'm following, but now I'm thinking back to Descartes. He had his motion, properly speaking,
Right.
and Newton has his motion relative to absolute space.
Exactly. It's like they're both trying to define what true motion really is.
Yeah, but they come up with completely different answers.
And not surprisingly, Newton's idea of absolute space, it wasn't without its critics.
Oh, I bet. I mean, it's a pretty bold claim.
It is. And the most famous critic of absolute space was Leibniz,
Leibniz.
who had his own very different view of space and motion. But before we get to that, let's talk about some of the objections that Leibniz and others raised against Newton's absolute space.
Okay.
So one of the main objections was about observability.
Observability.
Yeah, like, can we actually observe absolute space? Can we measure it?
I mean, it sounds kind of abstract.
It is. And one of the implications of Newton's own laws of motion is something called Galilean relativity,
Galilean relativity.
which basically means that the laws of physics are the same in any uniformly moving frame of reference.
Okay, unpack that a little bit.
So imagine you're on a ship that's moving smoothly across the ocean,
Okay, I'm on the ship.
and you're in a cabin with no windows.
All right, I'm feeling a little claustrophobic, but go on.
Now, you can do all sorts of experiments inside that cabin. You can drop a ball, you can swing a pendulum, you can do anything you want.
Okay.
But you can't do any experiment that will tell you whether the ship is at rest or whether it's moving at a constant speed.
Oh, that's interesting.
Yeah, all the laws of physics will behave exactly the same way in both cases, and that's Galilean relativity.
So how does this relate to absolute space?
Well, if absolute space exists, then there should be a way to determine your absolute velocity.
Like your speed and direction relative to this absolute grid.
Exactly. But Galilean relativity says you can't do that. There's no experiment you can perform that will give you your absolute velocity.
So if you can't measure it, how do you know it's even there?
Exactly. And that was Leibniz's point. He said, look, if absolute velocity is fundamentally unobservable, then why should we believe it's even a real thing?
Yeah, it starts to feel like a bit of a philosophical mystery.
It does. And then there's the question of, like, what is absolute space?
Right, like what is it made of?
Yeah. Even Newton himself struggled with this question. In his work, De Gravitatione, he hesitates to call absolute space a substance, in the traditional sense,
Because
because it doesn't seem to have any causal powers.
it's not like it's pushing or pulling on things.
Right. It's just this, like, passive background framework, and it also doesn't seem to be completely independent of God.
Oh, interesting. So we're getting into theology now.
A little bit, yeah. Newton suggested that absolute space is somehow dependent on God for its existence.
Okay.
But then again, it's not just a property of matter either, because Newton believed that absolute space would exist even if there was no matter in the universe.
Ooh, it's not a substance. It's not a property. What is it?
Newton ended up calling it a pseudo-substance.
A pseudo-substance.
Like something in between.
That sounds pretty vague.
It is. And Leibniz was not a fan. He thought this whole concept of a non-material yet physical entity was just incoherent.
Right, like how can something be both physical and not made of anything?
Exactly. And this led Leibniz to develop his own very different view of space.
All right, so let's talk about Leibniz. Now, the common understanding of Leibniz, at least when it comes to space and motion, is that he was all about relational motion.
Right.
Like, he believed that all motion was just relative, and that all relative motions were equally valid.
Yeah, that's the folk reading of Leibniz.
But our source, the Stanford Encyclopedia of Philosophy, it suggests that this is a bit of an oversimplification.
Oh, yeah. It definitely misses some key nuances of his philosophy.
Okay, so what's the real story?
Well, while Leibniz did emphasize relationships between bodies, he also believed in the existence of other quantities that were fundamentally real.
Okay.
And his mechanics, his physics, it implicitly depends on more than just relative positions and velocities.
So it's not just about where things are in relation to each other.
Right.
There's something else going on.
Exactly. So where did this idea of purely relational motion come from?
Yeah, where did that come from?
Well, it partly comes from Leibniz's arguments for the ideality of space.
The ideality of space.
Yeah, which is this idea that space isn't a real mind-independent thing.
Okay.
It's more like a conceptual framework that we impose on the world.
Okay, so how did he arrive at that conclusion?
Well, he argued that when we say a body occupies the same place as another body, what we really mean is that it stands in the same relations to other bodies that we assume to be unchanged.
Okay.
So a place is just what those two bodies have in common in terms of those relations.
So, like, if I'm sitting in this chair and then you come along later and sit in the same chair, we're occupying the same place because we're both in the same relationship to the chair, to the desk, to the walls of the room.
Exactly. And space, for Leibniz, is just the collection of all these places.
Okay, so space is not a container. It's more like a description of how things are arranged.
Precisely.
Right.
But Leibniz, he took this idea even further. He argued that properties are particular,
Particular.
meaning they can't be instantiated by different individuals, even at different times.
Okay, I'm not sure I follow.
So even though you and I might be sitting in the same chair, we're not actually having the same relationship to it.
Oh, I see. Because it's a different moment in time.
Exactly. So the sameness of place, that's something that our minds are adding to the situation.
We're kind of imposing this idea of sameness onto a reality that's constantly changing.
That's right. And that makes space itself ideal, not a real thing, in the same way that matter is real.
Okay, so for Leibniz, space is this kind of mental construct.
Right. It's a way for us to understand the relationships between objects.
But it's not a fundamental part of reality itself.
Exactly. And this brings us to the question of motion. If motion isn't movement through this real independent space, then how did Leibniz understand it?
Yeah. What's moving if space isn't real?
Well, for Leibniz, the key concept is force.
Force.
Yeah. He believed that force was more fundamental than space and time.
Okay, so we're getting into some pretty deep metaphysical territory here.
We are. So Leibniz, he wanted to ground his physics in a kind of revitalized Aristotelian metaphysics.
Okay, so back to the OG.
Back to the OG. So he identified primary matter with what he called primitive passive force,
Primitive passive force.
which is basically resistance to change and penetration.
So it's like the inherent stubbornness of matter.
Kind of, yeah, like matter's resistance to being moved or changed.
Okay.
And then he identified the substantial form of a body, its essence, with primitive active force.
Primitive active force, okay.
And these forces, they weren't just properties of matter, they were what constituted the very being of matter.
Okay.
And crucially, they weren't initially quantifiable.
So it's not like you can measure them?
Not at first, no.
Right.
But then, through the interactions and collisions of bodies, these primitive forces would give rise to what Leibniz called derivative passive and active forces.
Okay, so primitive forces lead to derivative forces.
Right. So derivative passive force would manifest as the different ways that materials resist being changed. And then derivative active force is a bit more complicated, but Leibniz seems to connect it to his concept of vis viva.
Vis viva? I've heard of that. That's like living force. Right.
Exactly. And this was a major point of contention between Leibniz and the Cartesians.
Because?
Well, the Cartesians defined vis viva as mass times velocity.
Okay.
But Leibniz argued that it was actually mass times velocity squared.
And that's basically what we now call kinetic energy, right?
Exactly. And Leibniz, he had some pretty compelling arguments for his definition. He showed how vis viva, defined in this way, was conserved in certain types of interactions. And it seems like he considered vis viva to be a manifestation of this derivative active force.
So for Leibniz, possessing vis viva was a kind of true motion.
It seems that way, yeah. It was a real distinction between having it and not having it,
Yeah.
and maybe even a way of quantifying this underlying active force.
Okay, so we're seeing a very different picture of motion emerging here. It's not about changing position in some absolute space.
Yeah.
It's about possessing this fundamental force, this vis viva.
Exactly. And this suggests that for Leibniz, everyday relative motion, the kind of motion we experience in our everyday lives, that wasn't entirely real.
Whoa, hold on. So you're telling me that, like, when I walk across the room, that's not real motion?
Well, it's real in a sense, but it's not the most fundamental kind of motion.
Okay.
Real motion, for Leibniz, was the possession of this virtus, this active force. And that's something that's fundamentally non-spatial.
So it doesn't depend on space. It's something deeper than that.
Exactly. And that's why this folk reading of Leibniz, the one that says he believed all motion is relative, that's just not the whole story.
Yeah, it's way more nuanced than that.
It is. And it's also why when Leibniz responded to Newton's scholium, the one about absolute space and the bucket, his response might seem a bit dismissive at first.
Right, because he kind of agreed that there's a difference between true and relative motion. But he didn't think that proved the existence of absolute space.
Exactly. But once you understand Leibniz's philosophical framework, his response makes a lot more sense. Because Newton's arguments in the scholium, they were mainly directed at Descartes' purely relational view of motion.
Right.
And Leibniz, he also disagreed with Descartes on that point.
So they were both anti-Descartes, but for different reasons.
Exactly. Newton, he wanted to replace Descartes' relational motion with absolute motion.
Okay.
But Leibniz, he had a completely different alternative in mind.
This force-based view of motion.
Exactly. So when Leibniz said that true motion doesn't necessarily imply absolute space, he wasn't just being contrary.
He had his own reasons.
He did. He had a completely different understanding of what true motion was.
So to sum it up, Newton, he sees true motion as motion relative to this absolute space, this fixed, unchanging background grid. But Leibniz, he sees true motion as the possession of this fundamental force.
Exactly. Which is something that's prior to and independent of space and time.
Wow. So we've gone from Aristotle with his, intuitive view of objects moving according to their nature
Yeah.
to Descartes with his unified space. And
Yeah.
it's